Good afternoon, everyone. I thank you to join this seminar. My name is Alberto Ortigo. I happen to be a fellow of the Institution of Civil Engineers and also a chartered engineer by the same institution. Our slope course is going to cover a few lectures, not just today, and we are going to cover several aspects of slope engineering. And the main references to what I'm going to present, it's on my books, which have been published long ago, the Handbook of Slope Stabilization, and also I'm going to refer to a few chapters of the soil mechanics in the light of critical states, theories. If you don't have a copy of this book, you just let me know. I'll send you a PDF copy, and this is important for this lecture. What you're going to cover today is, in addition to the course program, which I'm talking now, is landslide classification, geological factors, and also we are going to add risk assessment and debris flow. So let's get started. So the first chapter is going to be the first issue is going to be landslide classification. This is what we're going to talk now. First of all, the workflow, how we do landslide classification. First of all, we have to organize a site visit. This is absolutely important. And then what you do a geological survey, a topography survey, site investigation program, and mass movement classification. And then you may use geophysics. Boreholes and sampling in most cases are absolutely necessary, laboratory tests as well. And then you come up the last part is stability and risk analysis. Of course, with this, you may find the solution for this slope, what kind of reinforcement you may need or not, okay? In terms of workflow for soil rock, they are, of course, slightly different, but you have to look at drainage, surface protection against erosion. You may use anchor and bolts, especially for rock slopes, barriers, also flexible barriers. We are going to talk about this much later on. This is very important usually for rock slopes where we have loose blocks. And also here are some of the solutions that we may use for like cutback of the slope, reuse retaining walls, soil reinforcement, tied back walls, and soil nailing. And finally, in most cases, you have to design instrumentation alarm system. In some cases, just the opposite. And first of all, let's have a look at landslide types. This is in the book. It's a classification by Crude and Varnes from 1996, which we used. And these are type of movements like fall, topple. We're going to discuss this in more detail as long as we go through this section. Slide, spread, and flow. These are type of movement. Material types, we may have rock fall, rock topple, rock slide, rock spread, rock flow. Soils. If we have coarse soils, we may have debris flow, debris topple, debris slide, debris spread, and debris flow. If we have fine soils, earth fall, earth topple, earth slide, earth spread, earth flow. And these are some of the types in terms of geometry. We may have a circular failure, which we're going to, this is most common circular failure that we're going to discuss. If we have the rock very close to the surface, we may have a plane surface of plane failure of of soils. We may also, these are falling blocks. We are going to have example of this. Flow, sometimes flows is due rainfall on the top of a mountain, then it triggers this kind of flow until it spreads at the toe. Shallow failure or deep failure, and this is creep, also slow movements, which we are going to address later on. The most common failure is circular failure, and this is the kind of movement that may take place. And here are some characteristics of a failure. First of all, we have the crown cracks. Here's the crown, okay? This is the head of the circular failure, minor scarps, okay? And then at the toe, we have the bulging, or the material bulges in this at this location. I forgot to select the pointer. There's bulging at this location here, and this characterizes the geometry of the movement. Here's some examples. Here's some work where I have done this very long ago, in 1990s, in the south of South America. There was a big landslide which I had to analyze. In those days, were very difficult because slope stability programs are not as good as today. And these are kind of rotational slides. This is the city of Brasilia in Brazil in 1994. We had this was an excavation for the train line, and you have a lot of failures during the wet season. And also I did some work on this. This is a very interesting. Let me see if I can. No, it doesn't work. Why it doesn't work? Oh, no, sorry. Okay. A friend of mine sent me this, took place in the south of Brazil, and this is we see the landslide taking place, a major landslide along a highway. It's a rotational slide, a big one. Back to the pointer. Anyway, rock slopes. Rock slopes, the type of the failure is different. We may have plane failure if you have this kind of joint, planar joint. If you have two joints intersecting, we have a wedge failure. And we have rock fall or falling blocks. It is very common. We're going to see a few cases like that. Also, it's very in residual soils. It's very common that we have soils and toppled by loose blocks that we can either fix or remove or use barriers, which we're going to talk about that later. These are kind of planar failure. This is gneiss, and gneiss usually have relief joints, and these planar failure took place along these relief joints, which I did some work on that many years ago. And rock fall, very common in residual soils. I have faced this many times. This is a case of rockfall in La Carretera Sul-Americana in Ecuador. We have done some work on that in late 90s. Yeah, and this is a case that I got this from the internet. It's not an easy one, as you're going to see. Very interesting. Wow. And this could be prevented, as we're going to talk about that later. Okay, this is topple. When we have kind of a pillar of rock falling down like this. Okay, this is also very common. And this is a site in Portugal where uh, this kind of failure took place. As you see, you have a kind of vertical block that's sliding or toppling uh, like this. And this is also kind of toppling that took place in Carretera Sul-Americana in Ecuador during the work we have done there many years ago. And this kind of wedge failure also at Carretera Sul-Americana, as you see here, two joints intersecting and leading to a slide like this. And this is the kind of geometry that we may have in this case. Now, this is a very interesting uh, slide that took place where I used to cycle. I used to cycle almost every Sunday at this place, and once it's close to a very old fortress built by the Portuguese in the 16th century, and we used to cycle. There's a very nice place close to the seaside, and there was this big slide, unpredicted. I know because I have been there many times. Very difficult to predict this kind of slide. But anyway, it took place. No one was hurt, fortunately, and it's there. This very common mud or debris flow, which take place along a talweg on a mountain, okay, and usually due to severe rainfall at the top. Here are some cases. This one case I've been of our experience in a highway. This is also a very shallow failure, shallow slide that took place. The rock here is only 1-2 meters below the surface, and this kind of failure took place. Now, this is a very interesting case also from the internet, but it's a blast triggered slide. It's a mine in Turkey, and they decided to do some blasting at the top of the slope, and they're going to see what happens. Major landslides triggered by a blast. And this is work I have done last year in Morocco. It was a major landslide that took place at the slope. This is a big hotel, a resort called the Tomadou in southern Morocco. And there was a landslide in earthquake in 2023. We may talk about this later. The maximum acceleration was high, of about 0.18. And we did some analysis of this landslide, and we came up with some solution which would be nailing. We estimate the cost of the reinforcement, but unfortunately it did go ahead because the owner of the Tamador Hotel, also the hotel itself suffered damage due to this earthquake, and the structure was relocated in the end. I visited the site and also the Tamador town, which is not far. It's a couple of kilometers from this hotel, and I have seen lots of damage on houses in that area. This is shallow slides in which the rock surface is not far from the ground surface, something like 2 meters. This is also a shallow slide, which I did some work in 1990s. Tough times in which programs did not work. I did some work also in, if this is a town in São Paulo, in Brazil, which there was a major rainfall in 2000 and lots of landslides. Unfortunately, not many casualties, some 2 or 3 only. And there was a lot of work done after the this event and was part of that. These Andes in Ecuador, it's wrong written, have to correct. Ecuador. This is Carretera Sul-Americana. But this is a very high slope, something like 100 meters. This is tough because how can we stabilize a slope like that? It's an enormous cost. Anyway, this part of the work we had done in Ecuador in the late 90s. And this Andes, Peru, also just different because Ecuador has a very high precipitation level, high rainfall. On the other hand, Andes, Peru, on the Peruvian side, is much more dry. So this kind of landslide took place, and the position here at the bottom, although it's low rainfall rate. This is one major landslide also that took place. This is a historical town in the middle of Minas Gerais that comes from the 17th century, and lots of very old buildings from that time. And after rainfall in January 2022, a major landslide took place, as you're going to see. And this is very interesting. It destroyed one very old building, this building here, as you're going to see. This is called the Scaffold Hill, certainly because in the colonial times, Portuguese scaffold, but the Portuguese would hang people close to this site. This is also scary. This took place in 2023, and fortunately, did not affect population. This in the south coastal area of São Paulo, enormous rainfall of something like 600 millimeters in 24 hours. So it triggered lots of major landslides, as you see. Well, flow. If the flow is very slow, we call it creep. It's a continuous movement, undefined slip surface, and it has a drained behavior. Usually it takes place in gentle slopes, and we're going to show you some interesting examples of that. And if it's fast, we may call it body flow or debris flow, in which takes place in steep slopes, and I've shown you some examples. It's a viscous fluid that moves, and usually it has an undrained behavior, okay? Rapid flows, we may have earth flows, structural collapse of medium dense soils, and sandy takes place on sandy and silty soils as well. Pore pressure increase, mud flows, usually are very quick flows, rapid flows on sensitive soils, and debris flows, it's avalanches, rock blocks, soils, debris, etc. So let's go back to the pointer. These are kind of debris flow. They usually take place due to rainfall at the top of the slope. Okay, this is very, very common. Here are some examples which I had to deal with along my life. This one, debris flow, another one, 1990. This is the largest that I've known. A friend of mine, I'm going to refer to him, Professor Milton Kanji, gave me this example. He worked on all that. I didn't. So it was one of the largest debris flow ever that I have seen. About 200,000 cubic meters of material slide due to rain. We can also subdivide landslide by virgin or reactivated landslips, and landslip classification according to soil disturbance. We may have virgin landslides. They occur in disturbed soil with mobilized peak soil shear strength, or reactivated slides occur in disturbed soil at a previously occurring landslip surface with mobilized residual soil shear strength. Anthropic triggers, usually removal of vegetation, spill from water on sewage pipe, incorrect cuts, too steep, very common, very loose fills not properly compacted, and waste deposit incorrectly placed. Landslip triggers. This adapted from a publication by Guidicini and Niebla in 1984. Agents usually pre-exist in geology, morphology, climate, gravity, temperature, vegetation. And triggering before the landslide, rainfall, erosion, freezing, thawing, temperature change, solubility of groundwater, change in groundwater change, animal and anthropic activity, and triggers in general is rainfall, snow thawing, erosion, earthquakes, waves, wind, anthropic action. And causes can be internal, external, or intermediate. Internal cause, temperature change, shear strength decrease due to weathering. It's not very common. External geometry change, vibration, very common. I've shown you a very interesting landslide triggered by blasting. Intermediate, groundwater level rise, very common. I'm going to talk about that later on. Suction reduction, water filling joints, rapid drawdown piping. These are the main causes. And landslip triggers. Landslide, this is in the book as well, table 6, landslide trigger mechanism adapted from Varnes. Action, load increase and strength decrease, okay? And the effects could be removal of soil or rock mass, surcharge, seismic loads, horizontal pressure, strength decrease, material characteristics, changes of variable factors. This is rare, not common. Any phenomenon present, removal of soil rock mass, usually due to erosion, landslip cuts, surcharge, weights of rainfall, ice, snow, natural deposition of soils, vegetation, building structures, embankments, seismic loads. I've shown you some earthquake waves. Shown you example earthquake, another one by blasting. Traffic is not very important, but usually earthquake and vibration, blasting would lead to that. Horizontal pressure, water filled joints, freezing, expansive soil. Could take place. Geotechnical characteristics, stress, and material characteristics. This is not very, very common. At least unless we are dealing with tailings, that we are going to talk later on. Variable factors, weathering, shear strength loss, groundwater rise. Flow. Usually flow, the slip surface is very shallow, usually less than 5 meters. Sometimes can be deep. If the slip surface is over 5 meters, we're going to show you some examples. Progressive, slow, accelerating, and post-failure, mass still moves. I'm going to show you some interesting examples of this kind of creep, very slow movements. And there's a classification also in terms of landslide velocity. It could be very high, would be in terms of meters per second, down to very low, centimeters per year. I've shown you a very high, which was a block, the fall of a block, which struck a car, struck a big lorry. Can be high, average would be in soils, etc. Very low should be creep, and we are going to address this. This is this landslide or a possible landslide. It was taking place very slowly, and we did some analysis. This took place in Costa Rica in 2000. And we used the site, we did some analysis of the major landslide. Landslide limits here is very big. And the possibility of mud flow is high, the consequences are high. And here, a town with over 10,000 people living here, which could be affected by this major landslide. We visited the site, this was many years ago, 2000. And this was the approximate cross section in which we have breccias, shales, where most of the slide took place, and it was moving slowly, but a very high, so it's something like 300 meters or 200 meters high slope, very difficult to work. And we did some recommendation. Lateral spread, when the surface material extends or spreads on gentle slope, the style of ground formation is often associated with earthquake shaking. You may have this is one of the most interesting cases I have seen in my life. The town of Santiago de Puriscal in Costa Rica, in Central America, and it's a very gentle slope. The slope is about 6 degrees, and despite of this, the whole city, the whole town, or big part of it, is moving very slowly, as you see in this cross section. And I visit the site, and sometimes we see cracks like this one here, okay, in the middle of the middle of the town. And I visited the church, and this church had been closed because it shows this was the mayor of Santiago de Puriscal in those days, and she invited us to visit the church, which shows large cracks, large damage due to this movement. And also, we visited another project that we did in Ecuador in 2000. I have shown you a few examples. We have it's about 10 people doing this kind of visit, and this is one of the most difficult types of landslide that I have seen in my life, which is described in the book. And so I was impressed. This the landslide of El Turi in Ecuador, and it's a big one. It's about, let's say, 3 kilometers wide or long, and some 4 kilometers or 3 kilometers wide. And this is the Pan American Road, Carretera Pan-Americana, which we traveled, and this slope moves in this direction. And here lots of buildings that have been built by this university, which were fully damaged by this, and this, the river and the bridge here. And this approximately the cross section, they call it by sandstones and siltstones, they call it Azogues Formation. And these are the university buildings, and here's the river. And if by going around the site, we see lots of damage to the houses. This is one of the videos that I managed to take from the location. And this is a very interesting picture in which you see the house is tilting and the owner tries to prop the the his house, a nice house, fortunately. And we see water soldiers at this. I visited the site at the top of the mountain. We see lots of water, so the water is very close to the ground surface. And we see this as well. The fence is tilting, okay, and this a tilting pole, which very important sign of movement. Okay, we did some recommendation, but this is, I don't think there's any money to solve a problem like this. Better to relocate the structure. And well, let me talk a little bit about uh, what I call a slope tale of two cities. During my lifetime, I spent time in China, mainly Hong Kong, where I could learn from their experience with slopes. And I could make a comparison in between Rio, which I grew up, and other place, Hong Kong, mainly. And this is one small part of the book. You may find more information there. This happens to be my Chinese name, which I'm very fond of. It's Onpato in Cantonese. It has a different pronunciation in Mandarin, but in Cantonese, Onpato. And this is Hong Kong, seen from Hong Kong Island. Lots of buildings and very little space in between slopes and buildings. And I'd like to talk a little bit first about Rio and then to Hong Kong, how we compare the slopes in both places. Rio is also similar to Hong Kong, in which we have little space in between buildings and the slopes. And most of these landslides are triggered by rainfall. And so this takes place in the summer where this rainfall takes place. The first account of this was by a Portuguese priest, Father Anchieta, in 1580. He reported rainfall, the levels or precipitation levels he had never seen before. And later on, there's a very interesting report in 1711 when the French pirate or admiral, I'm not sure, René de Gatouan. De Gatouan invaded Rio in 1711 during the Portuguese rule, and there was a battle, and there are reports that this battle took place in under a very heavy uh, rainfall. And he invaded Rio with 16 ships. And this is the map of Rio. And he's supposed to have entered this part from the north. And this was the small city of Rio at the time. And he won the battle against the Portuguese. And later on, he captured the Portuguese governor and demanded a ransom from the Portuguese and from the citizens as well. So one of the invasions that took place in Rio. And what's interesting is from 1906, 1924, there are many reports of floods during summertime, and these are some of them. As you see, this 1906, 1911, 1924, and I have done in the past a lot of work for flood control. In 1966, it took place the Laranjeira slide, which took about 200 lives. And there was a big landslide, and the landslide knocked down a building that was here. I visited the site a few times. I remember I was in school, about 17 years old, and it was a Sunday evening, and I went to a party to a club nearby my house. And for the first time, it was 2 blocks away, not very far. And I had to come back walking, but with water up to my knees. I still remember that. And we had that night 140 millimeters in 24 hours. And we had about nearly 200 casualties in the city. And then on the next morning, or the next day, the Mayor of Rio created what we call today the Rio, which is an organization to look after the slopes to avoid this kind of catastrophe by the Rio Town Hall. And what the Rio does, slope stabilization works, design review of anyone building close to slopes must submit the design for review for foundation, slope stabilization. They have a risk reduction program, risk mapping, and the Rio Watch Alarm System, which I'm one of the creators of this system back in 1996, 97. And we are going to discuss this a lot in the last lecture, which is going to cover instrumentation. And some of the works that GeoRio has carried out, like this, not easy to go up here to the Christ the Redeemer, and they put up these buttresses with anchors, rock anchors, and this Cantagallo Hill also. There's enormous buttress here to avoid falling of this block on these buildings. They put a lot of drainage works, like drainage channel like this in Rio. This not far from my home, there was a big landslide here. They put tieback walls, drainage, etc., etc. And from 1996 to 1998, no severe rainfall, no severe accidents, people relaxed. Then a major landslide took place on the Lagoa. Fortunately, not anyone was, no casualties at all, but lots of property were lost. Like car, this was a car park, about 15 vehicles here were destroyed. And also took place, this in the outskirts of Rio, a lot of landslide, but no problem because, far from population. This also in a place of Rio, but no big problems with this. This is very close to where I used to live. This destroyed the house of a friend of mine here. I knew him, he lost his house. And also not very far, not many damage. And this is also close to where I used to live, and a major landslide at the top. And what's interesting, after that, they put drainage channels to increase the factor of safety of the slope, to avoid the water ingress into the ground below. And there was a loose slab, and then they put up this scaffold, very high, 150 meters high scaffold, the highest I have ever seen. And they did this kind of bolting to avoid the falling of this slab. The other thing that took place, this was a major problem for it was a small landslip, but with major impact to the city was the part of the Rebouças tunnel, in which 2007 was a small landslide, but we had a major consequence for the traffic in the city. So after that, lots of work have been done to increase the factor of safety of slope porches. Hong Kong, also lots of buildings close to mountains, and this is Hong Kong Island, and I used to live not very far this is Kowloon Peninsula. I used to live somewhere here. This is the old Kai Tai International Airport. Now it looks like they transformed this is in a park. and lots of slope problem. And in 1977, they had the Poshan landslide, also killed a lot of people. I don't know how many. And this also triggered the formation of the GEO. So it's a very similar story. After a major landslide, the government and the people of both cities, they decided to improve the safety and they created an organization to deal with slopes. This is a view of the Victoria Peak from Hong Kong Island, and some accidents that took place 1994, 1997, 1992 Kennedy Road, and I was there in 1996, and I was introduced to the Hong Kong alarm system, which they created a few years before, and they had a major rain gauge network. They had automatic rain gauges sending data to the GEO. The GEO is somewhere here, Geotechnical Engineering Office of Hong Kong. And this kind of alarm system was very successful in Hong Kong, and they came up with the decision level. The decision level, when the rainfall reached 100 millimeters in 24 hours, they issued alarms for people not to be close to slopes, to go to safe areas, and this was very, very, very successful to the point that after the accidents that took place after the alarm were reduced a lot. So we decided to copy this to Rio. I brought this idea to the Gel Rio, and this idea flourished also in Rio, which I'm going to talk more later on. Also, the Hong Kong, they do a lot of retrofitting of slope. I've been to a few, I visited some sites of slope retrofitting, like this one. They improve the quality of the drainage system. They saw mainly soil nailing walls. And how can we do a risk reduction program? That's what the GEO does, and that's what the GeoRio does. What's interesting, these two organizations were independently uh, born, and in the end, they were doing similar things. And now I managed to work with both. Foundation stabilization design review, inspection, they do a lot in Hong Kong, risk mapping, stabilization work, squatter clearance, they do a lot, and I visited a few of the last places where squatters were clearly were taken to much better homes, and the alarm system as well. This is Hong Kong. So this we finished this part of landslide classification. Now we are going to talk about next. And now we're going to talk about geological facts. But before we start, I'd like to draw your attention to two things. In every presentation, in the end, I have my email and my phone number. So if you need those books, or you didn't have access to those books, please let me know, and I'll be very happy to send you a copy. I'd like to tell you that my friend, Professor Milton Kanji, we worked together on many projects, including this book. This part of the book, he helped me a lot. We wrote together, but he had COVID and passed away in 2021 due to COVID, which was terrible. But anyway, I'm going to talk about geological factors that intervene in the how the slope behaves, and I'm going to talk about we have igneous or magmatic rocks, sedimentary rocks, metamorphic rocks, Just a second. Oh, no, sorry, let me put the pointer. Metamorphic rock joints, very important, and weather products, which are residual soils, etc., and also sedimentary soil. So here an example from Peru, jointed hard igneous rock forming blocks. Okay, this is an example of igneous rock blocks, hard rock boulders and blocks separated by weathering. This I've seen all my life, many situations like that. Here is an example from Tarija in Bolivia, cemented sandstones with subhorizontal joints. Okay, and this sedimentary rock profile in which we have sandstone and siltstone, very soft weathered shale from Tarija in Bolivia. This is from Minas Gerais in Brazil, weather phyllites. This is a big problem. This slope has been retrofitted long ago, but I managed to come here before most of the works took place in the last 20 years. And this is the kind of material. So we have a very different layer material, which a very different strength in this direction as opposed to that direction. And we would have to test this on using an imposed failure plane, kind of direct shear test, in order to analyze the strength on the through this direction here. And this is weathering profile of gneiss. So sometimes we don't have many joints. We have jointed rock here, but here saprolites, and this is topsoil. And weather products. Let's have a look at what are structured soils. This is a very interesting picture in which we see here the we see here the mature of the residual soil. Here's a young residual soil, in which we see the joint system, and here's the rock, okay, the weathered rock. So, geological features that we have to take into account: faults, joints, bedding, schistosity planes, stress relief joints, tension cracks, sheared planes, and weak layers. Let's see some examples. We have here jointed rock, okay. This from Cerro Verde mine in Peru. You see forming blocks, and also lots of blocks and also wedge failures, like here. Here, weather layers in jointed gneiss from Cubatão, São Paulo in Brazil. And as you see here, jointed gneiss. This is one of the failures that I've shown you before, which took place as a slide through along a relief joint. This is a very interesting overhanging slope in Angosto Passarre in Bolivia, cemented sandstone. And this how these features intervene in the geometry of the landslide surface. This is a circular slip surface where if we don't have the joints, this is how it takes place, okay? But if we have a horizontal layered material, this is the kind of failure surface that may take place. Inclined layer soil. If we have dip greater, the dip is the inclination of the joints. If the greater than the slope, this is the kind of surface that we may have. Or if you have the dip less than the inclination of slope, we have the daylighting failure in which the joints are going to come out on the slope. On the other hand, we have complex cases like this one, with lots of joints, difficult to analyze. If we have this kind of joints, okay, which I'm going to show you a very interesting experience I had back in 1967 in Rio. And this was the suburban slides that I did some work. These are two roads. They are, let's say, 300-400 meters apart. 400 roads, suburban roads on the slope. The slope goes down this way. And this is the kind of failure that took place. And what's interesting, how this happened. Someone who lived in this area here had a nice house in this area, phoned someone from Geological at the time. Look, my house is moving. And then they started doing some work, and they did some work for a long time. A very interesting case, perhaps the most difficult case I have ever had in my life to analyze a slope. And the suburban slides, this happened later on in 1988. 1967 was the first slide. This, it turned out again to happen in 1988. The movements increased. And this time, Geological went there and put instrumentation. They tried to understand what was going on. They had surface marks, they have inclinometers, but the movement was so large that they sheared the inclinometer tubes. And this is more or less what happened. This road failed. There was a big road. There was a tieback wall here, which failed. And this was before. And when I visited the site, this, of course, had taken place. And I still remember seeing one of these inclinometer tubes which has been sheared. And people thought this was a kind of creep. And the initial idea was creep and what to do to reduce water level. And what happened was that difficult because this is jointed rock, very high water level, okay? And this is a collusion. So in the beginning, no one knew what to do. Then they put some walls on the upper road and started to rebuild the site. And until a friend of mine, who is a geologist in Geological, decided to carry out some inclined boreholes. Why? Because he thought it was very strange why this was almost horizontal, and there was another part here horizontal as well. And then he decided to put some inclined boreholes. And what he found, a diabase dike, a sound, not joints, diabase dike in the middle of this jointed rock. And that was the reason for this formed a barrier, water barrier, so the pore pressure was very high here and much less on the other side. And until these inclined boreholes, no one knew what was taking place. So what was found by these site investigation with inclined boreholes was a kind of family of diabase dikes. They were some 100 meters apart, and this was the explanation for this landslide. This amazed me because the very difficult to to detect unless we carried out these inclined boreholes. And so from that time on, I always had my preferred geologist accompany me to help me to analyze these very difficult landslides cases. Okay, let's finish this part. There's the next one will be risk, but I'd like to make a 5 minutes interval, okay? And I come back in 5 minutes just to have a rest. Okay, let's go ahead. This is the final part of this seminar, in which we're going to address risk assessment, and also we're going to talk about debris flow. Well, risk management has 5 steps on the risk management process, which is identify potential risks, analyzing the risks, evaluating the risks, treatment of the risk, and monitoring and review the risk. These are managed process. So the idea, what we need to do in terms of slope, is to pull the risk level to an acceptable value of low or depending on the consequences. Okay, uh, so risk assessment depends on the likelihood of the slope failure and the consequences. So if you have a certain likelihood, okay, even though if the consequences are small, you may have minor risk assessment, minor risk. On the other hand, if even if unlikely, but the consequences are very severe, that's where you have to do anything possible to avoid avoid the risk, reducing the risk. So this is risk assessment. So vulnerability analysis. So there's a ranking and of low, medium, and high risk in terms of, and which are the main factors: the soils, slope inclination, rainfall, vegetation, anthropic process. Soils or rocks, of course. Okay, so this is the risk origin, and we can have low, medium, or high. And these are weights, and vulnerability ranking is the sum of all weights. Okay. Vulnerability mapping is usually is carried out on a scale of 1 to 20,000, 1 to 25,000, okay? And this is going to take into account occupancy, geology, surface deposits, whether the surface deposits or not, slope angle, okay? 3 or 4, usually we tend to use 3 or 4 levels of risk, and typical scales are 1 to 1,000 up to 1 to 30,000. But usually, vulnerability mapping, we use a scale of that sort: 1 to 20,000, 1 to 25,000. And this is an example of the municipality of Rio, in which we see the red areas, scale of 1 to 10,000, where the risk vulnerability can be very high. It's important to differ vulnerability to risk, because risk mapping, you have to take into account the detailed information, the properties, etc., the consequence of the failure. And this can only be carried out on scales of about 1 to 2,000, much more detailed scales, 1 to 2,000, 1 to 1,000. These are the scales in which you can include detailed information, properties, previous landslips, risk areas, risk points, and usually we adopt 3 levels of risk, and this is a typical scale for this kind of problem. Here an example of work we have done long ago, some 10 years ago or more, of 1600 kilometers of railway lines. This was the area, and this was the railway areas that we had to do this kind of work. And the consequences of on railways, the consequence of a failure, you can see this, what happened on the slope, although the inclination was okay, steepness was okay, due to rainfall, we had this slide, the consequences of slope were very harsh, as you see. And also the other points that we looked was attention to tunnel portals. Tunnel portals is also always a big problem in which we have to avoid the consequences. And the other thing that how we operate in this case, we had 2 field teams. The field teams, we had 1 geologist, 1 technician, and 2 or 3 people in the office receiving the data. And what we have done, we had access to the topography of the railway. This topography was supplied by the client, in which we had a range of 50 meters on both sides of the width of both sides of the railway. And this team visits the sites, carrying out classification. And what kinds of criteria in order to classify the risk, this vulnerability? Slope angle, inclination of slope is absolutely very important. Ground quality is very, everything is empirical, but ground quality was very empirical. We had some criteria which is not detailed here, but for instance, when we have loose blocks, etc., we always classified in quality 3, which had a much higher risk, especially in terms when the slope angle was high. And also we took into account these are some geological risk, and also we took account the rainfall as well. But most of this area, the rainfall could be very high. And what we have done, which was very interesting, we tested it in a previous work. The first part of the work was to calibrate this model along 100 kilometers, which was selected by the client. And we did something like that. We classified all the slopes into 1, 2, 3, 4, 5, 6, 7 classes. Most of them went up to this class here. And we did this for these 1600 long railway line. And this was very important for the clients to analyze the investments they could carry out in a 4-year program to reduce the risk, especially those which we had higher risk, like this one, for instance, a steep slope, very close to a river, this possibility of loose blocks as well. These I don't remember, they were, when we did the work, they were already carrying out stabilization work through soil nailing, etc., etc. So it was a job that took us nearly 1 year to finish, and a very successful job, for the clients to plan the investments in the next 4 years. And this is something interesting that sometimes we use, is the travel angle. This was some work done in Hong Kong, in which they have debris flow and sliding. These are it is one of the sites I visited in Hong Kong, the Castle Peak Road, and in function of the landslide volume. And these are the works that have been done by my very good friend who passed away, Professor Milton Kanji from São Paulo. He did a lot of work on debris flows, especially in São Paulo. And these are data that this is in the book. And what we see here, the slope angle that leads to debris flow is something in between 30 and 50 degrees, the slope inclination. Here's lots of slopes that he analyzed. Okay, the functional drainage area. Interesting that very large drainage area, very little risk. Usually drainage area is up to 4 square kilometers, and sort of inclination from 30 to 50 degrees. And He also did a lot of work on debris flow travel reach, his height over length, okay, uh, length, reach, and debris volume, okay, in which, so he got this kind of correlation. And here's the equation he got, the travel reach in function of the debris volume. And also he worked on the debris flow triggering precipitation, in which this is accumulated precipitation in millimeters, this time in hours, and he came up with this equation for the lower boundary. He did work on many slopes, not only Brazil, but other cases like there are some Venezuela, etc., etc., Antofagasta, Serra das Araras, etc. And this in the book, this is a summary of his work on how to obtain susceptibility grades of debris flows. And you add weights for rainfall, slope inclination, riverbed inclination, basin area, height of slopes, land use and vegetation, geoindications, which quality of ground, okay? And here the weights, and if we, he came up with this kind of equation in which we sum up these numbers and the weights, okay? And so the debris flow susceptibility, calculated values of susceptibility grades, SG intervals from 0 to 100. So if you have 0 to 15 is very high susceptibility, and if you have values between 80 and 100, the susceptibility is very low. So this the work of Milton Kanji. And I'd like to address this probably the major landslide I've ever seen in Venezuela in 1999. And this took place at these Vargas Mountains, close to the coastline. And these are the areas that were affected. The precipitation was something around 800 millimeters in 24 hours, enormous precipitation. And the consequences were very harsh. I visited the sites. Uh, see, sorry. Okay. This is what happened, landslide areas. Okay. And in terms of debris flow, lots of locations. And the reach, they destroyed big part of properties along this place in the coast of Venezuela. And sedimentation, what takes place? Let's see a few locations I have visited in 1999. Consequences, enormous consequences. It's supposed that 30,000 people died in this major landslide. You see the harbor, all the containers, they were moved. This one of the sites that I visited, this our car, you see the size of blocks that were transported by these major landslides. And some of the consequences, what's interesting, my friend that invited me to visit the site, lived in one of these buildings. And on the night before, he was in his brother's home back in Caracas, and his brother told him, "No, no, you're not going to leave because you drank a couple of beers. You have to stay here." And that's what saved him, because his building was his home was destroyed. And so that's it for today. You have my email, my phone number. Should you have any additional questions, should you need the books, access to the books, and if there is any question, I'll be happy to answer. That's it. Chat. Let me see if there is any. Okay, not yet, but if anyone would like to ask any question, I'm available. Okay. Or later on, you may send me an email. Thanks for the participation.